And then we just suddenly changed tax and we went to linear algebra for some reason. But I don't want to. But I want to sort of get back to what our main, the reason why we are doing it, so as to motivate it. So today I want to get back to Taylor's theorem and uh, how we can use it, the approximation up to the quadratic term with a cubic error term, how we use it to study maxima and minima. Because that is one thing that you did in your first analysis course for one variable calculus. And our brief is for differential calculus to see the analogs of whatever you have done for one variable and discover new phenomena, which is what roughly we have followed so far. We defined the derivative, chain rule, and etc. So Taylor's theorem. So let us go towards studying maxima and minima, and then we will see why all this business about self-adjoint operators, etc. Why it is required, where it is required. So first, reminder about one variable version. So reminder.
Sir, could you start the recording?
Yes, I will do it. Thank you. Okay, let's do that.
Recording in progress.
Okay, so we want to study maxima and minima of multivariable functions. The function itself will be real value because I'm calculating maximum or minimum, but it's a function of several variables. Okay, so first let us recall the one variable situation and how we can use Taylor's theorem to get a criterion. So this is something that you should know. So first, and so for a C3 function, in a neighborhood of some point A in R. So it's a function of one real variable, real valued function. So what do we have in a neighborhood of R? We have f of A plus h. So by Taylor's theorem, it is a C3 function. So we will get a quadratic approximation and an error term of degree 3, right? So let's just write this down. This should be familiar. So f of A plus h will be f of A plus f prime of A times h plus 1/2 f double prime of A times h square plus what is the third term? Then we can write it down. 1/3 factorial times f triple prime. It's a C3 function, right? So we can write this term. So what is the error term? So if triple prime not at A, but at some point between A and A plus h, right? So let us say of something. Some point between A and A plus h. Exactly what is not really important. The point is that this term is going to be multiplied by h cube, correct? So we will call this the error term or remainder term r of h. And what is the point? This r of h is cubic. So in particular, if I divide it by h square, it is going to go to 0. So let's take this and we will divide everything by h square. but I want to go towards maximum or minimum, studying local maxima or minima. And we know that at a maximum or a minimum, what has to happen? Come on. So this is one
The
variable.
first derivative goes to 0.
Yeah, the first derivative is going to be 0, right? This is a C3 function, remember. So in particular, it's differentiable. So we now ask this backwards, right? So if we suppose we have a critical point, which by definition, we mean that the derivative vanishes, then can we test whether it's a maximum or minimum or maybe neither? So let's recall the second derivative test. So now suppose that f prime of a is equal to 0. So that is to say a is a critical point. So RH by h square. All right. So let's do a little bit of calculation. F of a plus h minus f of a. And now we will divide this by h square. So this term has gone away. So because of this has gone away. So I simply have 1 half f double prime of a. H square has also gone away. And now I have the remainder term divided by. So let's recall what we said about, what you did earlier about the second derivative test. So what happens if the double derivative at the critical point is positive? Then what do we know about that critical point? Come on, this is something that you've been doing for years.
It's a maximum. It's
Uh,
minima.
if
It's a minima.
it's a minimum, right?
Yep.
And so let us see why. The point is, the point is this error term I can bound, right? So, and divided by h square, it is going to go to 0. So because in a neighborhood I can make this small, I can simply make it, I can find some neighborhood in which this is going to be smaller than the first term. Remember, f double prime a is positive. So I can make that, I can make the highlighted term smaller than that. And that will tell me that the right hand side in this neighborhood is going to be greater than 0, because the second term cannot overcome the first term. And that means the left hand side is also greater than 0 in that neighborhood for values of h in that small region around 0. But that precisely says that f of a plus h is always has to be greater than f of a. In other words, f of a is locally a minimum value. So let me write that down. And while I'm writing this down, the reason for doing this is that I would like to have a multivariable version of this. So you can think about what we need to do. We still have Taylor's theorem, but what the difficulties are going to be. Okay. All right. So then f has a local minimum at a because so formally I can do this. Choose delta greater than 0 such that whenever h is smaller than that in absolute value, this r of h by h square absolute value is smaller than so then the right hand side is going to be greater than 0 for all h such that straightforward, right? And so for h in this window, f of a plus h is going to be greater than f of a, which is to say that f of a is minimum value of h, value of f in um, the neighborhood, or in, yeah, so in the neighborhood a minus delta to a plus delta. Okay, so this is what we would like to imitate in multivariable version. So let us go there. By the way, so it should also say similarly, if f double prime is less than 0, then f has a local max at a, and you can do a proof similarly, or just apply this to apply whatever we did to minus a. So want to do this, want to find for multivariable situation. So we should start by writing out the Taylor expansion for a C3 function, and then see what we can do. Multivariable case. By the way, so what happens if the double derivative is 0?
So we have to check higher derivatives and then
Right.
depending
So,
on the
I mean, so then the double derivative itself really cannot tell us. Okay, so this means we should write the multivariable Taylor's theorem. And we saw that, said appropriately, the multivariable Taylor's theorem, understood appropriately, is really the same as the one variable Taylor's theorem. We just have to understand these steps. So let's write this down. I don't think I can get it on the same page, but okay. So here is the situation now. Now f is a function from open set U in Rn to R, a C3 function. So what does Taylor say then? F of a plus h is equal to f of a plus f prime of a times h. Does that term still make sense?
Yes, sir.
Yeah, it makes sense. Oh, I should say where h is. Sorry. Then h in some small neighborhood, some open neighborhood. I think we called it W. No? W of 0. We first have a plus h lying inside U, so that I can apply f to it. And okay, what is the next term? So f double prime of a 1/2. And now h square doesn't really make sense, but I can think of f double prime of a applied to the point h comma h. Understood suitably. Right? And then we have the error term. The error term says, or rather the remainder term. So what does the remainder term say? So this is 1/6 times f triple prime of something. Where is that something, by the way? Because we just do this by applying one variable Taylor's theorem, right? On the line, straight line joining a and a plus h. Because I have an open set, I can find a small enough ball around it so that, which will be convex. So the entire straight line lies in the domain. And then I just apply to the composite function. So this is going to be something between a and a plus h. So let's say between really means not in the sense of real numbers, but on the line joining the two, and evaluated again at h comma h comma h. So perhaps let me put this in quotation marks. So at least this part, because we do want to write it the way we wrote it in class. Um, right. So how when you actually write it out, what is it? F of a. What is the second term? F prime of a times h. What is that? So written as a matrix, F prime of A is of what dimensions? The function is from something in Rn to R1. So the derivative at A as a linear map will also be from Rn to R1. In other words, its matrix will consist of a single what?
Row.
Row. Okay. So I can write it as the following. So this is going to be uh, D1 up to Dn and H1 up to Hn. So let me just make a notation over here. So where d1 simply means the partial derivative of f at the point A. So let me just say this. D1 of f at A. So this is just shorthand. Okay. Plus the second one will be, what will that be? So let me write this down as a summation. So half will still go, and then it is going to be di dj of f evaluated at A times hi hj. And I and j independently go from 1 to n. And similarly, there will be this third term, which I will not write down. So let's just call this R of h. If you want to write it out, what will it be? It will be summation of di, of dj, of dk of f evaluated at some point between a and h, multiplied by the scalar hi, hj, hk. But the point is, what do we know about it? We know that this remainder is, so R of h. What do we know about it? How do we bound it? This is less than or equal to?
Can you explain that second term again?
I'm sorry, say that again, please.
Can you explain the second term?
Okay. But I mean, this is exactly what we got in Taylor's theorem, no?
Okay, so that it's the same expression.
It's exactly the same expression. So the only thing that I have not done is that, okay, if you recall, let me see if I can just, no, maybe let me not go back. You see, if this is a C3 function, so in particular, it's a C2 function. And so D1, D2, the value of D1, D2 on F at A is going to be the same thing as the value of D2, D1. And I can combine those terms. But let me not do that. Right? I can combine that term and I can write 2 times a single term. And that 2 will cancel with the outside 2. So if you remember all that expression, the general expression, d1 to the s1, d2 to the s2 divided by the product of si factorials, that expression was obtained by collecting like terms using the equality of mixed partials. But let me not do that. This is what we obtained when we straightforwardly applied chain rule by precomposing the given function with the straight line function uh, from closed interval 0, 1, which takes t to a plus t times h. Okay, so what do we know about the remainder term r of h? It is less than some constant times
The norm of h cubed.
norm of h cubed. Okay. And yeah, so of course I can say absolute value. Do I have to put norm on the left? What kind of entity is R of H?
It's a real number.
It's a real number, no? Because we have taken a real valued function. So everything that is written over here in this expression, these are all real numbers added to each other. But they're obtained, the real numbers are obtained using multivariable quantities. Okay. So now this is the kind of interesting thing. So let's, where, okay. So let's now try to write this in a form that is more compact. So this is going to be f of a plus. Now this next one is often written in terms of the gradient vector. So what is the gradient vector? It really is the same as the matrix of partial derivatives, which is a row vector, but I simply take transpose of it. One way, I mean, one reason maybe is because then now it's a vector in the same vector space, right? I can regard it as such. So we can write this as d1 up to dn, and now the inner product of this with h1 up to hn, right? Okay, and then the next term I will write shortly, but we can say it like this. So f of a plus what is the expression? So this is the vector that I call the gradient vector, the gradient of f at a. I believe we did introduce this terminology at some point, right? Even though we haven't used it, I think we did talk about this. So, and then dot product with the vector h. Now, in the third term, I would like to write something in a similar way, shorthand. So how does that come about? And then you see the following. So I can write this in the following. So this half is there. That's okay. But now this is what I'm going to do. h1 up to hn, I write it as a row vector. Then I write di dj of f at a as a matrix where I and j go from 1 to n, and times the column vector h1 up to hn plus r of h. So I sort of pulled this out of my hat. At some point when we were doing this, somebody in class mentioned that we could do this for the quadratic term. But let's just see what this is saying. So where does this come from? So let's write this. So check, see below. So let's just do this separately. Let's just do this in the case of n equal to 3. So what do we have? We have h1, h2, h3. And let me make a shorthand notation over here. Let me not write. So let's just write d11, d12, d13. Okay. So again, the notation is that d12 is d1 of d2 of f evaluated at a. Okay. So, and then d21, d22, d23. Times h1, h2, h3. So just see what happens. So let's just first multiply the so let's say this is h1, h2, h3. This is a matrix, okay, not product. And times I'm going to get a single column vector. So what will be the top entry? That's d11 h1 plus d12 h2 plus d13 h3. And likewise, right? So I'm going to get a second row and the third row at the same time. But when I multiply, what happens? You see, now now I have a single row times a single column. So I'm just going to get a real number. But what do the terms become? So the first one, for example, it says h1 times d11 times h1 plus h sorry okay so um, okay, if I really need to plus something or the other. See, the dot dot dots are going to come h2. But the point is that so let's do this. So this, when I say h1, it now multiplies the entire first thing, right? So it will gives h1 d11 h1 plus h1 times d12 h2 plus h1 times d13 h3 and plus dot 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 plus dot dot dot. And you see exactly, I get exactly what I want. The every partial derivative, whether mixed or not, dij of f of a will get multiplied by h1 by hi on the left and hj on the right. The left right doesn't really matter. These are all scalars. So you see, I'm getting exactly the same expression that was written in the sum over. Okay, so I hope this is clear. There is really nothing going on, just keeping track of indices. Okay, so let's close this here. So how do I get to write this term? So this is 1/2 times, this is H transpose, right? And on the right hand side, I write H. And then I have this matrix here. So I will still write this as di dj of f at A, thought of as a matrix, times H. This is really just multiplication plus R of H. Now this matrix has a name. It's called the Hessian. So the Hessian matrix of f at A. So this is going to play the analog of the double derivative, right? So the f double prime, let's go back to the one variable situation. What was the thing? We said that if the double derivative is greater than 0 at a critical point, okay, we're talking only when the f prime is 0 at a point. Then we look at the double derivative and whether it is positive or negative. In those cases, I get to say that the function respectively at the given critical point achieves either a local minimum or a maximum respectively. So I want to say something of that type. So that's why the Hessian is important. But now we don't really know what it means for a matrix to be positive or a matrix to be negative. So let's introduce this. So Hessian matrix of F. So in order to define this matrix, I really just need to have double partial derivatives. So let F be again a function from an open set U in Rn to R. I need to be able to calculate these double derivatives, these double partial derivatives. So such that, well, F is C1 first of all. Why does F need to be C1? See, I want to be able to calculate all double partial derivatives. That means the first partial derivatives have to be differentiable. Okay, the first partial derivatives have to have all partial derivatives. But in order to have partial derivative, in order to be able to calculate these partial derivatives, the functions have to be continuous, no, in each direction. That means the first partial derivatives all have to be continuous in particular. But that makes the function C1. So F is C1. So that means that all the partial derivatives del f by del xi or di are continuous on U. And we want to say that f double prime exists at E. And therefore, all the di dj. So components of f double prime are di dj of f at a. So in that case, the Hessian is the above. Then the Hessian is Hessian. Let's not even say matrix. The Hessian of a, Hessian of f at a is the square matrix, precisely this di dj of f. Just based on what I have given so far, does this matrix have to be symmetric?
No, sir.
No, because I do need the second partial derivatives to be continuous. So if f is C2, then this matrix will be symmetric. With I j entry that. Okay.
Sir.
So let me just say this. When f is C2, the Hessian is symmetric. Okay. Yes, somebody had something.
Yeah, so why should f be C1?
Okay.
I mean, you want we want the partial derivatives for the partial of the partial derivatives to exist, but that can happen without the partial derivatives being continuous.
Okay. So what does it mean to So what does it mean to calculate? Okay, so let me just say this. What does it mean to calculate, let's say, d1 of d2 of f?
We first find
Or, right? So let's say all the di's of d2 of f I want to calculate, right? That means d2 of f has to be a, in order to be able to calculate, directional derivatives of any function. Okay. So let me just, sorry. So d2f has to be differentiable in every single direction. But okay. But that does not necessarily mean that the function d2f as a multivariable function needs to be a continuous function. Is that what you're saying?
yes, sir.
Right. Okay. Um, right. But you see, okay. But if okay. But I'm going to apply the Hessian only for a function or at least as far as I know at the moment. I'm going to apply Hessian only to a function that has a double derivative at a.
Okay.
But if you have a double derivative of a at a, the total double derivative, in that case, f prime has to be continuous, no, in order to calculate its derivative.
Yeah.
And in that case, the partial derivatives have to be continuous, because f prime itself has to be continuous.
Yes, sir.
Right. But as to your question, whether this is a necessary condition even to contemplate the Hessian, I think it's a valid question, but I don't know enough to say anything more. So let me not say anything. But in any case, see the Hessian, I want to apply the Hessian when the function is not even C2, it's even C3, because I'm going to be using Taylor's theorem in order to have some criterion for maximum or minimum. All right, so at this point, so X. So work out some examples. And maybe, in the context of the question that also she just asked, we have spent some time, and even in the exams I asked you about, whether a function has to be like this and has to be like that if these conditions are met. Does f have to be differentiable if all partial derivatives exist? If all partial derivatives are linearly related to all the directional derivatives exist and are linearly related to partial derivative, etc., etc. But you see, in practice, the focus is going to be on nice functions. Many times the functions will not just be C1 or C2, they will be C infinity functions, because the functions that we deal with commonly they're going to be like polynomials or exponential functions, trigonometric functions. Those are going to be really, really nice functions. Okay. So you can take some polynomials maybe and work out some examples. And we will at some point when it comes to applying this and actually calculating maxima and minima, we will have to do this. So what is our goal now? We make the same definitions as before. So let me goal.
So
Yes.
just one more follow-up question. If the function is not nice, like if it's not C1 or C2 or something, is it like we don't talk about maxima, minima, or I mean, like we need to use S?
Okay, but now you see, I mean, that's a very valid point. A function having a maximum or a minimum has absolutely nothing to do with its derivative. I mean, a priori, right? We are just seeing whether the function is the largest in some neighborhood or globally. The function could be completely horrible. So it's not that we don't talk about it. It's just that this is a tool that in nice situations, calculus helps us find these things.
Okay.
Right? I mean, it's a perfectly valid question to ask. All right, so, okay, so the goal is now the form. Before that, might as well write down some definitions. So I want to study maxima or minimum, but we already said that. So let's define critical point. So f is f, let f be a C1 function on open U in Rn. So sorry, that sentence is not very well constructed. So, all right. So we say that A in U is called a critical point if f prime of A is equal to 0. And what kind of 0 is that? It's not the 0 number, it's the 0 operator. Or if you want to think of this in terms of the gradient by taking the transpose, then it's the 0 vector in Rn itself. So is it again correct to say that this C1 function, if it has a maximum or minimum at any point, local maximum, then f prime has to be 0 at that point. Is that correct?
It needs to be differentiable.
Yeah, but I have taken a C1 function.
Oh, okay.
Right? So just check, no? Because if I follow this function in any direction, so notice that if f has a local max or min at A, then it has so in all directions. So if I consider this function along any line, then the restricted function along that line, that's just a one variable function, differentiable function. Over there also it has the point has to be a local maximum or a minimum, and that just means by one variable calculus that the directional derivative in that direction has to be 0, right? If at A, then along any line through A, okay, again, so also again a bad sentence being formed. Also the same must hold. And hence all directional derivatives must be 0 at by one variable calculus. In particular, all partial derivatives must be 0. And because I have taken the function to be C1, the partial derivatives will determine all the directional derivatives. So So this makes sense that if I want to find candidates for maximum or minimum, then again, I just look at the points where the gradient is 0. So, so I will just say that delta f at A is equal to 0. Remember, the derivative and the gradient are not the same thing. They're just transpose vectors of each other. Okay. Now, in one variable calculus, we could use the second derivative in order to tell whether a function has a maximum or minimum at a critical point, provided the second derivative was positive or negative, right? It was not 0. Then we could say something that, then we could say something. So what is going to be the analog of the second derivative being 0 or non-zero? That means I have to look at the Hessian matrix. Now, the Hessian matrix, whether that entire matrix is 0 or not, is not how we are going to determine it. So this is the definition. So if now f is C2, if f is C2, then a critical point A is called non-degenerate. If the Hessian is if the Hessian HF is non-singular. In other words, the determinant of this HF of A, remember it's a square matrix, right? So I can take its determinant, and the matrix being non-singular as an operator is really the same thing as the determinant being non-zero. Okay. So the theorem is the following. If f from open U as usual, open U in Rn to R is a C3 function, and A is a non-degenerate critical point of F, then F has a local minimum at A if and only if. So I want to say that H is somehow just like in the one variable case. I want to say that that means that H is somehow positive. So what is the notion of positivity over here? So this is saying that H is positive definite, which, what does that mean? So let's look at H. H is a symmetric matrix, right? This is a C3 function. In particular, it's a C2 function. So all the mixed partial derivatives, they do not depend on the order in which I'm taking the derivative. So di dj of f at A is dj di of f at A. So what do we know about a symmetric matrix? So this positivity is really to do with eigenvalues. Okay. So this is a symmetric matrix. What do we know about its eigenvalues?
They're all positive. They're all real numbers.
They're all real numbers.
Yeah.
So you see, if you do not know that in advance, then what does it mean to say that an eigenvalue is positive or negative if it's a complex number? Real matrices can very well have complex eigenvalues, right? Because that characteristic polynomial could have complex roots. So H is positive definite. So which is to say, one equivalent characterizations, all eigenvalues of H are positive. And in exactly the same way, F has local max at A if and only if H is. So you see, F has local maximum at A if and only if, that just means that minus F has a local minimum. The Hessian of The Hessian of minus F will be the minus of Hessian of H. So if I take the negative of a matrix, then all of its eigenvalues will just become minuses of what they were, right? So this is going to be called a negative definite, which is to say all eigenvalues of H are negative. So you see, this is where we needed that result, that the eigenvalues of a symmetric matrix are guaranteed in advance to be all real numbers, and I can diagonalize that matrix. So this is where that linear algebra enters the picture. All right. So this is the reason. So this is why we wanted to study. So this is the reason why we want to study. So H is non-singular. Let me just say that. Did we write this somewhere that H is symmetric? Okay, so why we want to study? And their diagonalization. So okay, so now let me ask you the next question, because Hessian is symmetric. So if this is the case, then the next question is, but everything is real over here, right? Why do we then want to study all this Hermitian business if all that we are interested is this? Why do we care about those, Hermitian form, which is linear in one variable, conjugate linear in other? Why do we bother with that?
Maybe so we can define the same thing for Cn.
Yes, we can. But do you recall how we proved that the eigenvalues of a symmetric matrix are real?
We assume that they are complex and that a priori.
Right. But you
Yeah.
see, the only proof that I know of this passes through considering Hermitian matrices and sesquilinear forms. Forms that are linear in one variable, and conjugate linear in the other variable. And the form itself, when you switch the variable, then it becomes conjugate of itself. You see, this is how you show that if the eigenvalue is lambda, then it is also equal to lambda bar. Go and see this proof. It's a one-line proof, but that is how, at least that's the proof that I know of, showing that the eigenvalues of a self-adjoint operator are real. So I don't know of at least any straightforward way of showing that, okay. And then you can apply this to a real symmetric matrix because it is in particular self-adjoint, right? I can think of that real matrix as a complex matrix. So you should go and see that one-line proof. And at least I do not know of a simple way of showing that the eigenvalues of a real symmetric matrix are real. If we just say that, no, I don't know what a complex number is, then the result still makes sense, right? That a symmetric matrix can be diagonalized, working entirely over real numbers. That's still valid. Yes. After the fact, you see, I do not have to know about complex numbers. I have a real symmetric matrix, then I can find invertible matrices. In fact, orthogonal invertible matrices, right? That I can diagonalize this matrix by means of them. So there are no complex numbers in the statement. But I don't know of at least a simple way of any simple way, or in fact, at this moment, I don't recall of any way of showing that the eigenvalues are real without looking at them as complex matrices, Hermitian, complex matrices of that are self-adjoint. Okay, so this is where we want to go, and so now there are a couple of things that we could do. One is that we could simply say, look, the linear algebra that we want, we have a very clear result that we want from linear algebra. We will just take it as granted and we will go forward, or we will pause our development and prove whatever we want. And I'm looking for some kind of direction from you here. My preference would be to say, let's not interrupt the development, because we are proceeding in a systematic. We're developing calculus, we define derivatives, and we are doing analog things. We prove Taylor's theorem. Let's do maxima minima, and whatever we require, we will either black box it, or we can just say, well, this is how you prove it. But I would rather not go into a digression on just linear algebra for its own sake at this point. So here's one thing. So one point is the following. If V is a inner product space, then positive definite operators on V. So that is by definition those self-adjoint operators with all eigenvalues positive. We know they are real anyway because the operator is self-adjoint, but they should all be positive. So they are in one-to-one correspondence with inner products. But you can say, well, wait a minute, what do you mean? V is already an inner product space. It already has an inner product. But you see, on the same space, I can have many inner products. So all inner products are obtained by means of applying a positive, so there is a one-to-one correspondence. If you are given one inner product, then every inner product will be obtained by using a positive definite operator on V. Okay, so I'm sort of in two minds about where we go next. And so I mean, do people have any kind of preference? I would prefer just to do maxima and minima and constrained optimization, Lagrange multipliers, and do the linear algebra as required, rather than continuing what we did last time and saying, okay, let's just study these self-adjoint operators and see what positive definite operators are. If you have any opinions, then maybe you can communicate to me. So why don't we I was just trying to see if I can conduct a poll now. Let me not. So maybe discuss among yourself, and if there is some kind of dominant view in the class, then please let me know. Okay. And where we go next really depends on what you tell me. So I would like to just stop today. Okay, maybe what we can do is we can do the what I asked you to do in 2 and 3 dimensions, which is to say, okay, what are orthogonal operators in 2 and 3 dimensions? I asked you to do that, no? So we could discuss that. Any comments or any suggestions from anybody? Or any questions? Okay, so here, let me just draw a line over here. It's just discussion. Discussion of and so what's an orthogonal operator? I.e., given by matrices matrices, let's say P such that P transpose is equal to identity. So in R2, what are what are all such operators?
Rotations about the origin and reflections about lines to the origin.
Correct. So let's try to prove this. So, but what does this equation mean? So PP transpose equal to identity, which is exactly saying that the rows or columns, because this equation is equivalent to saying P transpose P is identity, that the columns of P are what?
Orthonormal.
Are orthonormal. So it is much easier to do this geometrically, right? So let us say that P is equal to VW as column vectors. So we know that the columns are orthonormal. So as an operator, what is P doing? So as an operator, P sends E1 to V and E2 to W, and they have to be orthonormal. So let's just look at this. This is E1 and this is E2. And let's draw a separate copy of R. So the vector V is going to go somewhere. So let us say this is V. It has to go to a unit length vector, right? Because lengths are preserved, right? This is an V and W are orthonormal. So where can W go? How many choices are there for W?
2.
There are only two possibilities for W, right? So V must be perpendicular to W. So let me just write this down. Norm of V is 1, norm of W is 1, and V dot W is equal to 0. So our V is perpendicular to W. So possibilities for W are either, this is one possibility for W, or so possibilities for W. Only possibilities for W. So let us call this one as number 1 and this one as number 2 cases. So what is in case 1, what do we have? So let's just draw the x-axis over here, x-axis. And let me not draw the y. Okay, let's draw the y-axis also. So what do we have? In case 1, what does the matrix P have to be? What is this vector V? V is exactly equal to cos theta sin theta, where theta is this angle. It's a unit vector, right? So that's what the vector has to be. So we have cos theta sin theta. And what is the second column?
Minus sin theta, cos theta.
Right? I mean, you can just look at this, minus sin theta. But what is this matrix? Or you can just see what is it doing to both basis vectors. It is rotating both basis vectors through angle theta, counterclockwise. Since there is an operation that is clearly linear, that matches, that does the same thing to the basis vectors, it must do the same for all other vectors. So it's rotation. Rotation through theta. Okay, case 2. What do I get? Or P is equal to cos theta sin theta, and then sin theta minus cos theta. All right. So, by the way, what is the determinant of the first matrix?
1.
And that of the second?
-1.
Right. So this is orientation preserving. Right? That's what we. So what is this second case? This is kind of interesting. So the geometry of this is something that is worth understanding. So can we understand this geometry? Well, anyone?
Sir, it is a reflection by the line passing through x-axis and v at angle theta by 2.
Okay. So here is the thing. Unfortunately, I drew this angle. So too small. So let me draw a separate picture. So the idea is that, okay, so here is one, at least this is how I'm thinking. So this is E1 and this is V, correct? Maybe I should have called them, so you see, poor notational choice. E1, E2, then a correspondingly better choice would be V1, V2. Or you can use EF and VW. This kind of schizophrenic thing, but anyway, I'm done. So E1 is going to V. So one thing is, if I draw this line over here through angle theta by 2, then at least, and if I consider reflection through this dotted line, that think of this dotted line as a mirror and reflect every vector in this dotted line, right? Then is it clear that this is a linear operator? Yeah, because all the parallelograms will reflect. Is it clear that this is an orthogonal operator? Yes, because all lengths and angles are preserved by this. So this is a valid candidate. And certainly it matches on E1. What does it do on E2? So now it is a matter of checking that E2 is also going to, that E2 is also, because you see, okay, so let me see if I can do a reasonable job here in this picture. Let's draw a different colored line over here. So if I draw this line over here and think of this as a mirror, then notice that E1 and V are symmetric around it, but as are E2 and the second possible position of W. Do you see this? Sort of maybe turn your head a little bit and see that they are also reflections of each other. So I'll just say, see that. And the reflection in the red dotted line, I have E1 going to V and E2 going to position or option 2 for W. For W. Okay, so this is a reflection. So this brings in other interesting questions. So we just showed that any orthogonal matrix is either a rotation or a reflection. But product of two orthogonal matrices is orthogonal. So this then asks us, geometrically, can we understand that the product of any rotation or reflection with another rotation or reflection? By product, I mean composition. You know, when you mix matrices and operators, you can mix product and composition, but one should speak clearly. Yeah. So the composition of two rotations is a rotation. That is clear visually. So that leaves us with composition of two reflections and composition of a reflection with a rotation. So this is something that you should work out geometrically on your own. Okay. So work out uh, reflection, sorry, reflection composed with reflection. So reflection 1 composed with reflection 2 equal to what? And reflection composed with rotation equal to what? And also rotation composed with reflection. So it's an instructive geometric exercise that you should absolutely do. And there is a little hint, no? If you think of the determinants or orientation, example. For rotations, the determinant is 1. For reflections, the determinant is -1. What does that suggest? If I compose a reflection and a rotation, what should I get? See what's happening. So, because I'm going to be multiplying a matrix that has a determinant 1 with matrix that has determinant -1. So I'm still going to get a reflection. Do you think the order matters? Reflection followed by rotation and rotation followed by reflection. They will both give me reflections, but will it be the same reflection? Something to work out. Okay. Also, this is interesting. What happens if I take the composition of 2 reflections?
Sir, no, sir. Reflection and rotation do not.
Will be a rotation, right? Because what the determinants both will be -1. They will get multiplied, and you will get 1. So you should work these out. And
To answer the question you asked before, no, sir. Reflection and rotation cannot combine. For
right.
example, we can just multiply the 2 matrices on top on the screen now, and we notice that they don't.
Right. So if you just take, in fact, they will rarely commute. So so you should figure out exactly what happens. Okay. All right. So yet another exercise. All right, so here is yet another question. You see, mixing algebra and geometry and playing back and forth is always a fun thing. Now, suppose I do not do this geometry. Right? Suppose I work only algebraically. PP transpose equal to identity. Now, you see, if I have, okay, so matrix of what is the matrix of a rotation in a suitable basis? Of course, what do I mean by suitable basis? So along mirror and orthogonal to the mirror. So if I take a vector that is orthogonal to the mirror, then what will it get sent to? Come on, let's just take a look at this one.
Negative of that vector.
Negative of that same vector. So along mirror, let's call it a different vector now. Let's call it U1 and U2 is orthogonal to the mirror. Okay, so U2 is orthogonal to the mirror, so it will go to minus of itself. And what will U1 go to? A vector along mirror, when I reflect in the mirror, it stays there. So this is, so this means that for rotations, the eigenvalue, for reflections, the eigenvalues are 1 and -1. What about the eigenvalues for rotation? Are they real?
If it's not the identity or like minus the identity, then no.
Correct. In fact, you can just see it. No, if there were a real eigenvalue, then that means that vector would get mapped along the same direction, and in fact, it would have to get mapped to itself or minus of itself. right? Because it's a rotation, you see. So the moment I have a rotation that is other than through 0 degrees or through 180 degrees, I'm not going to have real eigenvalues. But you can sort of see that, no, that matrix of the rotation. Okay. So eigenvalues, so reflection has eigenvalues 1 or minus 1. Sorry, 1, what am I saying? 1 and minus 1. Reflection has non-real eigenvalues unless theta equal to 0 or 1. In which case I get the identity matrix or the minus of the identity matrix. Oh, okay. So our time is done. So let's stop. But you should absolutely do. So this is really just sort of the warm up. I mean, it is nice in itself, but it is fairly simple. But this is a warm up exercise to go to the next dimension, which is R3, and then see what happens. All right. So you should absolutely carry this out for yourself if you have not done this so far in life. Okay. So let's stop the class. Maybe we can continue the discussion afterwards.
Recording stopped.
If I can figure out how to conduct a poll. So anyway, I'll figure this out for the next time. So okay, what happens in R3? So I again have my standard basis E1, E2, E3, and that will go to an orthonormal basis. Yeah, and let's call them F1, F2, F3. But it is not so long, not so clear any longer, no, because this orthonormal frame, it's going to go to some other orthonormal frame. But can we understand this geometrically, what this thing is doing? So any ideas?
So at least one matrix would have to be about an axis, like in, let's say, the XY plane about the Z axis, right? So that we would have like it would be a 3x3 matrix with let's say 1 in the top right corner, and then the usual 2x2 rotation matrix about the angle, like
Right.
theta in the bottom left corner.
Right. So sorry, just let's come to that. But somebody had just Soham has just pointed out that I wrote the wrong thing over here. So let me correct that. I think I said the right thing, but rotation. Okay. All right. So sorry. So say that again, please.
So like at least one transformation that I guess would be good to have is rotation about, let's say, fixed axis. So let's say the Z axis is fixed, and that matrix would look like 1 in the top right corner, and then in the bottom left 2x2 block would be, the usual 2x2 rotation matrix.
Correct. Exactly. So yeah, and of course I can change the axis to have anything that. So is it clear that if I fix an axis in 3D, and if I have rotation around that axis through some angle, it is going to be an orthogonal matrix, right? Whatever that transformation is, because it preserves lengths and angles just visually. And so it is going to send orthonormal vectors to orthonormal vectors. So, okay. So the question is now, to what extent is this the general situation? And it is not going to be a general situation, completely general situation, because you have a reflection is also going to work. Now, in this case, a reflection will be through what? If I want to take a mirror in R3,
it should be a plane, right?
It will be a plane. So if I take reflection, then and again, I will be able to diagonalize it by choosing a suitable basis. What will the eigenvalues be? Yeah, so you see the two vectors along the mirror, if I choose any two orthogonal vectors along the mirror or any other vectors for that matter, they are both going to stay to themselves. So I will have a 2 by 2 identity block, and something that is perpendicular to it will get mapped to minus of itself. So this, by the way, this is the general analog of a reflection in a Euclidean space, that one hyperplane stays fixed, and something that is orthogonal to the hyperplane gets mapped to minus of itself. So it has all but one of the eigenvalues as one repeated eigenvalue dimension minus 1 times, and one eigenvalue minus 1. Okay. So unlike the real case, there is going to be something interesting about eigenvalues. This is a 3 by 3 matrix. So if I take the characteristic polynomial, it's a cubic polynomial. As a result, what are we going to have? Something about eigenvalues. Eigenvalues are roots of this polynomial. This is a cubic polynomial, a real polynomial.
There is always one real eigenvalue.
Right. There's always one real eigenvalue. What can it be?
It has to be plus or minus 1.
Correct, because you see this matrix, it sends an orthogonal basis to an orthonormal basis to an orthonormal basis. That's what PP transpose equal to identity means. So if any vector, it preserves length. So anything of length 1 has to go to a length 1. That means this eigenvector has to go to itself or minus of itself. Okay. So now here is the sort of the thing. If necessary, I can multiply this matrix by minus identity. Just take minus of it to ensure that one of the eigenvalues is 1. Or if you want, what you can do is you can switch 2 columns. Why will that ensure also that the eigenvalue is, if it was minus 1 first, then it will be 1 now?
Because your sign of your determinant has changed.
Exactly. So the determinant becomes minus of what it was. Correct. And that is going to be the, okay, so maybe, so 1 second. So that's the product of the eigenvalues, but you see the eigenvalues are not, okay. So, I mean, what I'm saying is correct, but now I'm not able to justify it except after the fact. So can we do this? If I switch columns, then one of the eigenvalue, real eigenvalue, if there was one that was minus 1, then it will become clear. Maybe not, but it's perfectly okay, right? I can multiply the whole operator by minus 1, and whatever had eigenvalue minus 1, it will now have eigenvalue 1. Now look at this direction. So I am of course going to choose this as one of the vectors to describe the matrix of my orthogonal operator in a nice way. So what do I do now? This is an orthogonal operator. So, and it is keeping this direction fixed. And remember, perpendicular things go to perpendicular things. Therefore, the plane that is perpendicular to this vector, whatever those vectors are, all of those vectors, where will the matrix send them to? The matrix that I started with.
So that plane has to map to itself.
That plane has to map to itself. Because remember, angle between two vectors, if the matrix is P, and if two vectors are V and W, then the angle between V and W is the same as the angle between P of V and P of W. Right? Because an orthonormal basis is going to an orthonormal basis. Lengths and angles have to be preserved. So since the vector, this fixed vector, let's call it F1. Since F1 is getting mapped to itself, whatever was perpendicular to F1 also has to stay perpendicular to F1 after matching. But now this becomes, now, so you see, now have this operator on the plane, and this is the point, the plane, the operator restricts to the plane. Everything in the plane is getting sent to the plane itself. And now this plane is a copy of R2. So I can apply whatever we said until now, I can apply this to this R2. You see how important it is to be able to say that a vector is not a tuple of numbers. Because I just want to be able to think of this plane as a copy of R2. If I actually insist on writing each one of those vectors as by its starting coordinates in R3, then it's not going to be as transparent. I mean, so what will happen is that this orthogonal operator, which maybe I took minus of that, it's going to have an axis, and then in the plane I am going to have either a rotation or a reflection. So if in the plane I have a rotation, then you see then the whole operator just becomes rotation around the fixed eigenvector. Everything I'm rotating around that. What if I have a reflection in the plane? So let's say my original vector was f1 and f1 is staying fixed, and in the plane that is orthogonal to it, I have a reflection. So I can choose a vector that is fixed by the reflection. Let's call that f2, and f3 goes to minus of itself. Then the whole thing becomes a reflection. Do you see? Reflection in the plane spanned by. Okay, so you see, maybe I'm just talking without right. So you should work this out for yourself. So f1 was fixed in the plane orthogonal to it. I chose vectors such that f2 was fixed and f3 got mapped to it minus of itself. So that means that the plane spanned by f1 and f2 has to stay fixed, because if two vectors are fixed, then any linear combination will also be fixed. And f3 will get sent to minus of itself. So everything will be reflected in f3. In the plane orthogonal to f3. Otherwise, it will be a rotation. So the result is again the same. Everything is going to be either just 1 second now. Yeah, no, but not quite, because I arranged the. No, I have to still take care of my initial operation. No, initially I took the matrix and maybe took minus of that matrix. Okay, so since I did not prepare this, let me not babble on. Let me just stop here. But this is something that you should absolutely work out for yourself. Any questions or anything anybody wants to say?
Sir, like if the directional for a function, like for all the directional derivative exist, and if they satisfy the usual thing, like
right.
Yeah, so the function needn't be differentiable.
Right, and in fact, as one of you pointed out, one of the things that we did. So a couple of you, I think, also wrote to me with examples. So that's great. But somebody also pointed out that one of the examples that we did in class, that itself works. Because what happens is that all the directional derivatives at the origin, they all vanish. And so then this condition that they must all be appropriate linear combinations of the partial derivatives, that is automatically true because it's all zero. But the function is still not differentiable, because if I come along a curve, suitable curve, then things do not work.
Okay, sir.
Right. Yeah, so now the question that I have is the following. So this is a question that I asked several of you, which is, I want the following. I want the same thing to be true in an open set. That is, I want a function. So let me write this question. Is it possible to have f, let's say, open U, even R real valued is okay, such that f is continuous such that for all a in U, f is continuous at a, dv of f at a exists and is equal to whatever. So a is equal to sigma lambda I ei and is equal to summation lambda I bi of f at a. So the function exists at every point. All the partial derivatives also exist at every point, and they satisfy the appropriate linear relation. Of course, such functions exist, I mean, but f prime a does not exist. And for good measure, maybe I want to say that f prime of a does not exist at any point. So if such a thing has to happen, then notice one thing, that the partial derivative, at least one partial derivative has to be discontinuous at every point. Because if all partial derivatives were continuous at a given point, then our proof would apply of, that proof with the path, walking along the path and taking, applying mean value theorem at every segment, then making the estimate and letting the path collapse. That argument would apply, and it would give me continuity of f. It would give me existence of f prime of a at that point, which would then imply that all the partial derivatives are continuous. So, sorry, what did I say? Just the continuity of partial derivatives at a single point will give me the existence of the derivative at that point. So, yes.
Yeah, so no, you'd asked me this question, and I in the midsem, I think I made a calculation mistake. You can't use the example we did in class. I mean, we can't.
Okay, I see. So, but I do believe that. So, I think the example that you said was that xy divided by square root of x square plus y square, right?
Yes, but I don't think that's correct.
Okay, so maybe there is a mistake, but there are other examples. So if I can just look at the email, you use the same thing. You you multiply some powers of x and y in the numerator, and you add appropriate powers of x and y in the denominator. We have done examples like this in class, and there was an example like that in the homework. If you just change the powers in such a way that all the directional derivatives just vanish, just by taking an up, just by increasing or decreasing the power appropriately. Now I don't recall. Does anybody recall what the example is? A couple of you sent such examples to me. So
I think x cubed y divided by x to the power 4 plus y squared.
Okay, so let me just write this down. So x cubed y divided by x to the
4 plus y squared.
Plus y squared. And of course, I define this as 0 at the origin. Right? So just check whether this works. But what I would like is that f prime of a does not exist anywhere.
This won't hold for any.
So what I would like to have, f prime of a does not exist for all. So this is for all a. Sorry. That this function won't be so works. So check. At a equal to 0, 0.
So do
But
you
you
want
see, but you see, everywhere else there will be no problem with this function. Everywhere else it will have a total derivative. I do not want this function to have the total derivative anywhere. But at everywhere, I would like it to be otherwise nice. It is continuous, and all partial derivatives, all directional derivatives exist, and they depend linearly on the partial derivatives. So you see the partial derivatives will have at least one partial derivative will have to be discontinuous at any given point. Some partial derivative will have to be discontinuous. I want this to happen in an open set. So do you see now? I mean, so this function somehow has to be bad everywhere in some way. Oh, DNE means does not exist. Yeah.
Sir, I have one more question, sir. So in the second quiz, there was a question. Yeah, the second question. We were
Yes.
given some conditions
Right.
of the partial derivatives and the directional derivative, and asked if such a function exists. So
Correct.
can you
And
discuss the
so
answer?
that was a mistake on my part. I asked a question that I did not mean to ask. So if you open the quiz, what I meant to ask was, first I wanted to ask whether such a function exists without the continuity.
Oh, okay.
Right? But then I meant to ask, see, I tried to combine two sentences into one and I made a question, unintended question. Then I meant to ask, can you construct such a function that is continuous at origin? And can you construct a function and does such a, so the questions that I had in mind were can you construct such a function, and then can you construct a function that is continuous at the origin? So when I was combining them into two, I forgot the phrase at the origin. Okay,
Oh,
and then
okay,
it's
okay.
and then it is a much simpler question, right?
Yeah,
It is quite possible to construct a function that is continuous at the origin. So now, if you want this function to be continuous everywhere, then it is not clear to me. But I think somebody showed me some examples of how one can do such things. You can try to sort of smooth the behavior. So the answer to that question, I do not know as I asked it. So, and I will correct it accordingly. So some people also said that that quizzes take too much time, as I said at the beginning. But I will take all of that into account when I assign the final grade. So don't worry too much. Yeah, anything else? Okay, good. So let's stop and we will meet on Wednesday. If you know anybody who has not had the exam, please ask them to get in touch with me today, if they have not done so already. All right, thanks everyone.
So Apratham here. I mean, we had a talk yesterday.
Right, exactly.
About
So
the
let's
exam.
let's just talk right after class, okay, on the phone.
Okay.
So,
thank you, sir.
okay, bye everyone.
Thank you, sir.